second. All right, hello again. Yeah, sorry, just trying to still get stuff a little bit sorted here. I mean, the good news so far is that that weird little error message isn't directly on the screen in front of everything, so that's a good start. But yes, hello. I'm Nathan, your friendly neighborhood PhD student. I'm come to talk about chemistry. Joining me today, at least for the moment, is the lovely Persephone. Just having a little snooze, and we'll see if she comes over to check us out. Had my lovely sound checker just make sure that you can actually hear me, because I don't know what I'm doing, and checking that myself is too technically difficult at the moment, but we'll get there. Anyways, so let's look at what we did earlier in the week last time, and just do a little bit of a recap. And then we'll keep going. We'll keep talking about chemistry and science and fun stuff. So last time we were going over some acid and base chemistry, and so we went over things like what ionic bonds are, polar covalent and non-polar covalent bonds are, and that these are all labels that are kind of arbitrary for things that don't super duper exist, but are useful. Because there's essentially no such thing as a bond that is purely ionic. The only examples of bonds that are purely covalent are between good God, what's the word? Homonuclear diatomics. That's the one. Where it's just two atoms of the same type on either end of a bond, such as hydrogen gas or fluorine, if you're brave and or stupid. So things like that, where there is no difference in electronegativity. Those are actually nonpolar. But that is rare and generally not actually all that useful. So we went over a few examples of what falls into those different categories, and a little bit about why. We did a bit about talking about inductive effects and how those affect polarity through bonds. And we talked about how to calculate formal charge. And so this just relies on taking the valency of the individual atom, because this is always looking at specific atoms in a molecule. And so going over the valency of them is just the number of valence electrons that effectively makes this element neutral, such as for carbon that's 4 electrons, for oxygen it's 6, hydrogen is 1, so on and so forth. So you take that valency minus the number of electrons that are actually surrounding the molecule in the structure, and to do that you split each bond in half, give 1 electron from the bond to each atom on either side of the bond, and that's how you count up those electrons. And so that's how we look at formal charge. And this question was dealing with exactly the same thing, and then drawing Lewis structures for various ions. I didn't do that because it just didn't seem interesting to me at the time. Now, This one was using curved arrows to show the flow of electrons for acid-base reactions. So we did a bit of that. We talked about how in these equilibria, the equilibrium will always favor the side of the reaction that contains the weakest acid. And then we got into a bit about like what makes an acid strong or weak, and so we look at the primarily we look at the stability of the conjugate base, and so then we talked a bit about resonance delocalization and how that can spread out the charge that is incumbent on a conjugate base of an acid, and that contributes heavily to the stability of the base. And then we talked a little bit, looks like we didn't draw anything, but we talked about how inductive effects also can help to stabilize those charges, because a charge that is more spread out is happier. We do not like to have focused charges, and anything that reduces the charge density is going to be a stabilizing effect. And then we went over a little bit about what resonance structures actually are, because resonance structures are not like different forms that a molecule adopts at different times. You can consider like all valid resonance structures exist simultaneously, and the actual molecule can be represented by a weighted average of the resonance structures based on how good or terrible they are. So primary example of that being benzene, whereas the position of the double bonds is irrelevant because the double bonds don't exist, because these are all intermediate. All of these bonds are intermediate between single bonds and double bonds. They have a bond order of 1.5. Then we got into a bit of just identifying which of the given compounds is more acidic and why. And again, this centers primarily around the extent of stabilization of the conjugate base. And then at pretty close to the end of the stream last time, got a lovely question about whether hydrogen bonding impacts the acidity of a compound. And I thought we'd start this stream off right with a correction, because I gave an answer that was not as correct as it should be. So, I had some stuff written down about it that I wanted to talk about. So, so his question was, does hydrogen bonding affect the acidity, or make something more acidic? And I said no, because I was largely thinking about like the intact molecule of acid with the hydrogen attached. We're talking about Bronsted acids, and so in that case, I do not think that hydrogen bonding would have a big impact on weakening that bond, or partially removing the hydrogen from the atom it's riding on. However, I ignored basically everything else I'd been talking about that day, in that generally we look at the stabilization of the conjugate base, and hydrogen bonding, in fact, for sure would impact the stability of the conjugate base, because if you picture something like on here, we've got an acetate. Sorry, that's not the acetate. That's the acetate ion. So just consider that the conjugate base of acetic acid. And if this was in water, for example, you would you could imagine seeing water being around, and you could imagine like an interaction here between the negatively charged oxygen and the hydrogen, because these all of these water molecules are polar. There's a partially positive charge on the hydrogens, and so instead of these electrons being essentially, ooh, that's a nice little pair. So instead of these electrons being like almost entirely localized on the carboxylate section of this molecule, if there was a hydrogen over here with a partial positive charge, like there would be in water, you could imagine that perhaps these electrons would come a little further out, because there is an interaction between the electron deficiency of the partially positive hydrogen and the electron excess of the carboxylate ion. And so that is, in a very real sense, spreading out the charge that's on this carboxylate ion. So absolutely, that would lower the charge density, make it a more stable conjugate base, which does increase the acidity of the compound. So that is entirely my bad for saying something silly, because I wasn't considering the entire system, and this is just kind of a thing that happens. People make mistakes. I make mistakes as much as anybody does, even though I have been studying this stuff for a little over 12 years, and this is entirely okay, because I guess this is effectively how we learn. If we ignore mistakes, or if we pretend we didn't make them in the first place, or try to rationalize them away, we don't really do particularly effective learning in that kind of a in that kind of a situation. So I think it's really important to just look at your mistakes with a critical eye, and because nobody enjoys being wrong. Doesn't feel great. But recognizing that you're wrong, and that you need to adjust how you're looking at things, that is a great thing, and this is this is the underpinning of the entire scientific endeavor. So I very much want to create a space, whether it's in a lab or a classroom, or here on Switch. Switch, very nice. Twitch, that one. I want to create an environment where it is okay to make these mistakes, because these things are going to be treated gently, and it's all right to make mistakes, because we're going to examine them and learn from them and do better the next time. So this has been my very brief TED Talk on screwing up and why that's all right. So, actually, on that as well, I do a fair bit of tutoring, and I mean it's just part of the nature of the thing that mistakes are going to be made, which is absolutely fine, because when mistakes get made in a tutoring session, that shows generally it shows. Sorry, how am I going to say this? So it shows me, the tutor, where the break in understanding is, because I always tell my students 95% of the time I don't need to do any imparting of knowledge to the students. It's not me just lecturing about these concepts and providing new information. It's about helping students to piece together what they already know, because generally um, they their foundation of knowledge, their knowledge of the basics, is perfectly sufficient to get to the right answer about these things, and so it's just really hard to see the whole picture and piece all those things together yourself when you're just going through this and learning. So somebody who's been at this for a long time, I've got a pretty good sense of the overall process, and it makes it really easy to find what we need to focus on when a mistake is made. So I often like. If we're going through like a reaction mechanism or something, and what I say is like just draw an arrow that is just wrong, or protonate the wrong thing, or whatever, and I'll just kind of let them go with it for a bit, or they might be a little nervous and like draw one thing and then turn around and ask me if that's right, and I'll be like, no. But like let's like keep going down this road, and then like we can talk about why that's not going to get you to the right answer. And I've found that to be a really effective way of solidifying these concepts. So, anyways, this is me just rambling on. So I think it's time to actually do some chemistry for a bit. Alright, so just kind of pick up more or less where I left off. More or less where I left off anyways. Okay. Okay, so again, we're looking at these pairs of molecules and trying to figure out which of these is more acidic. So the hydrogen on the structure that is drawn, we're assessing the acidity of that hydrogen. And so again, with this, we assess the acidity by looking at the stability of the conjugate base. So for each of these, we're going to draw, this is the thick boy. Let's do that. Ooh, that's gross. Okay, so deprotonate the nitrogen, which has a lone pair that they didn't draw, and we get this negatively charged nitrogen. So this is the conjugate base of that secondary amine. Secondary meaning just just meaning that it's attached to two carbon groups. So two carbon groups and one hydrogen makes it a secondary amine. Versus, we actually don't need to draw anything there because that's just a carbon, and now it's a carbon with a lone pair. And spoiler alert, we don't love that. Okay, so looking at these two, we were assessing the stability of each of these conjugate bases, these charged species, and from this there's a very clear winner over here in the nitrogen with the negative charge is vastly more stable than the carbon with a negative charge, and this is because of the electronegativity of nitrogen. So when we're talking about a negative charge and like stabilizing it, I think we need to talk actually about like what a negative charge is. That might seem a little basic, but that's where we're going to start. So a neutral atom, because let's just start with an atom here. A neutral atom has an equal number of protons and electrons. So for a nitrogen, there's 7 protons, and 7 electrons in a neutral atom of nitrogen. Because they're just each of them carries a +1 charge for protons, -1 charge for electrons. So when those are an equal number, they cancel out. Now, when you have an extra electron, so an N minus would have 8 electrons, and of course here I'm including the core electrons in my count. So it would have N minus would have 7 protons and 8 electrons. Put a little minus there, a little plus there. So versus a C minus would have 6 protons and 7 electrons. Okay. So when this is the case, when we've got a negatively charged atom, the extra electron is being held like quite loosely by the atom that we're talking about. So it's because it's not a balanced state having an extra electron, because this introduces like this high charge density to the atom, and so the more electronegative the atom is that is negatively charged, the tighter it's going to hold on to the electrons in the outer shell. In this case, and this includes like the quote unquote extra electron. So there's going to be more attraction, more force between the higher electronegativity atoms, the nucleus with the more protons than. I messed that sentence up. There's going to be more attraction between the electrons in the valence shell and the protons in the nucleus for an element that is more electronegative. So if it's being held tighter, it is less inclined to share that electron in the outer valence shell. Versus a lower electronegativity element like carbon is not holding very tightly at all to that extra electron, and it is this holding the electrons loosely that allows it to be reactive, because electrons that are held very tightly to a nucleus are not super inclined to go and do chemistry, and so it is exactly this lower attraction between the nucleus and the electrons that causes the reactivity. So that was long. So let's just keep going on that. So between carbon and nitrogen, the nitrogen is more electronegative, and when we're comparing two atoms in the same row, which carbon and nitrogen are, they're both second row elements, then the deciding factor in acidity and the stability of the conjugate base is going to be the electronegativity, which is closely tied with that effective nuclear charge, the attraction to the nucleus that the outer electrons feel. Okay, so here we've got a proton on an alkene and a proton on an alkyne. So the conjugate bases here are that was a very long bond, and that was not chemically accurate. Okay, so Now we got a lone pair on that carbon. Versus this one we've got linear bond. So deprotonated alkyne looks something like that. Now, the stability of the conjugate bases here. It might seem at first that they should be, pretty similar, but they're really, really not. So the negative charge in an alkyne is stabilized by the presence of these multiple pi bonds, because there's an effect called the anisotropic effect, which helps to stabilize and again spread out the negative charge, and this is fairly effectively done. Sorry, fruit fly. This is effectively done by a triple bond, and vastly more so than it is with a double bond. So this ends up with the pKa of an alkene is something like 40 to 45-ish. I do not know the exact number off the top of my head, but it's something around there. Whereas the pKa of an alkyne is around 25, which is an enormous difference. Recall that the pKa scale is a logarithmic scale, so this is some 15 to 20 orders of magnitude more acidic. The proton on an alkyne as compared to the proton on an alkene. And notably for these, there is absolutely no resonance stabilization for either of these molecules. Again, the alkyne is stabilized by the anisotropic effect, which I'm not going to get into right now because I don't want to. But the alkene is effectively not stabilized at all. So this is very much skewed towards the alkyne is vastly more acidic. Okay, so let's look over here. So we have got this be benzoic acid and cyclohexanoic acid. So the main difference between these two being that the benzoic acid is attached to an aryl ring, so there's going to be a great deal of resonance stabilization, versus the cyclohexanoic acid is just going to have like the two resonance structures for the acetate group. So very quickly draw those out. Okay. So now for resonance structures. Okay, so let's show some resonance. So we can move a lone pair on the charged oxygen, form that into a double bond to the carbon. But in the formation of that bond, that would make 5 bonds to carbon, and that is a cardinal sin. That is a big no-no, so we don't do that. So we have to break a bond to that carbon, and the only one that we can break is the pi bond in the carbonyl. The other thing that we can do here. Can we actually do that? I'm sorry, my brain has stopped working. Give me one moment. Can you tell I don't actually do any planning of what these sessions are going to be? That's actually on purpose, because this is not intended to be me like lecturing or just being a talking head. Because this is intended to be like kind of an interactive session, and eventually it will be. So like I'm more inclined to like keep it open to having people ask questions, having any particular concepts they want to go over. I'll always have these problem sets that I can that I'll be happy to go through when it's a matter of filling time. But yeah, it's just problem sets, and it's just me kind of just doing a thing, really. So. Sometimes you'll look at a chemical structure and you know that there should be more resonance, but you just can't see it. That's kind of what's happening now. Yeah. And if you're going through like an undergrad in chemistry, if you're going through OChem and you happen upon this, maybe you can feel good about yourself that someone who's close to finishing a PhD, sometimes my brain just stops working too, and just is what it is. Okay. Because like technically we could, it's not. There we go. Color coding. So like we could do that, but this is going to introduce, in fact, 3 charges onto this molecule, which is really bad. Actually, would be probably such an atrocious resonance structure that it wouldn't actually do anything. It's like what I'm gonna do is I'm going to go to a good old pKa table and just see if there's actually a big difference in the pKa's of those two things. So, okay, selecting carboxylic acids. So we got C6H5, which is the aryl ring, so it's the case of benzoic acid. It has a pK of 4.2. And of course, this is not going to have a cyclohexanoic acid. So that's not particularly useful at the moment. It's got one but not the other. Yeah. Okay, so this pK table doesn't actually have it. So, ooh, caps, very nice. I don't want to yell at Google. Let's see if we can find it. Cyclohexane carboxylic acid. Yep. Okay, so the top result in Google at least says 4.9 for that versus 4.2 for a benzoic acid. And that's actually not a whole lot of difference. So this may have, in fact, more like very slightly more stability, but not by much. So these may actually be very close to even. I wonder. Okay. All right. So, what I'm getting from this. So this is 4.9 to 4.2 pK between cyclohexanoic acid and benzoic acid. That's a pretty small difference. Much smaller than we'd expect um, for uh, for something that's uh, much more resonance stabilized than another. So here's my thoughts on this. I do not think that there is actually any resonance stabilization into the aromatic ring. So it seems like it is still like it's still got the resonance stabilization of the acetate group that's left, but but you know what? Okay, so one thing that we'll go over when we eventually get to talking about NMR spectroscopy, because NMR the chemical shift of different signals depends heavily on what it's attached to. Excuse me, and is greatly affected by electron withdrawing or electron donating properties, and things that are attached to an aryl ring, even when there is no resonance stabilization, even when there is no resonance possible here. Okay, just a minute. Okay. So in an NMR spectrum, you would expect like these hydrogens to be significantly more downfield compared to these hydrogens. And by downfield, I mean like things that are shifted downfield have like they are more. It's called de-shielded, which say that there's less electron density around these groups, so they are de-shielded and appear downfield. So these would be higher ppm. Because specifically because of the influence of the aryl ring, because aromatic rings are like they all else being equal, they are intrinsically electron withdrawing, and that is what I suggest is more stabilizing in the benzoic acid versus the cyclohexanoic acid. Because but this is specifically an inductive effect. It is not a resonance effect. It is similar actually to is the anisotropic effect that we see in alkenes and alkynes, other pi bonds, or things that are adjacent to pi systems, and that inductive withdrawal when we're talking about there's a negative charge on this carboxylate group, and we have some inductive withdrawal into the ring. That is going to be an inherently stabilizing effect, and so that's why this benzoic acid will be the more acidic, although not by much. That's a weird song, but yeah, much better. Okay. All right. Okay, so this is a good one. So these draw the conjugate bases. minus. Okay, so of these two, the much more stable one is this one, the alkene, and that is because the conjugate base is resonance stabilized. So we got a lone pair adjacent to a pi bond. And note that this is very different from this situation where you got when the anion is part of the pi bond. Oh, my writing is so good. Okay. Exclamation point. Okay, so this one has resonance stabilization. We can push that negative charge onto this carbon. And that spreads out the negative charge quite effectively. And again, resonance effects are very, very powerful in delocalizing charge and stabilizing anions, and cations, of course. Stabilizing ions. So, compare that to... compare that to this compound, which has exactly no resonance stabilization. Like if we try to form a double bond there on this carbon, this would form a fifth bond to the carbon next to it, but this one has no bonds that we can break. No, it doesn't have any pi bonds, so you'd have to kick out an H minus or a C minus or something else. And also, very importantly, it then would not be a resonance structure. You cannot, resonance structures cannot change the connectivity of a molecule. They can only change where pi bonds and lone pairs reside. So if you're breaking a single bond, it's no longer a resonance structure. It's just a different molecule. So doing this is completely impossible. That negative charge is fully localized on that terminal carbon, which is sufficiently terrible that it pretty much would not happen. The only situation where you could actually feasibly do this would be treating it with lithium metal, and you form an alkyl lithium reagent, which are phenomenal bases because they're extremely reactive because they hate to exist. Same alkyl lithiums, but anyways, yeah. So no resonance stabilization possible. It's not a stabilized charge whatsoever, and it is the that makes this the weaker acid. Okay, so looking at these two, again, of course, we're going to have the conjugate base will have that resonance stabilization of the carboxylate group, but the only difference here, so the difference between these two molecules is the halogens, the fluorines versus the chlorines. And so the stronger acid is going to be this one with the fluorines for a couple reasons. So fluorine is more electronegative than chlorine by a substantial amount. Chlorine is somewhere around 3 or 3.2 electronegativity, and fluorine is 4. So fluorine is very significantly more electronegative. It is, in fact, the most electronegative element on the periodic table, according to most ways of assessing that. One moment. So just by the electronegativity argument, which is saying that the fluorines are going to have a more powerful inductive effect. So when there's a negative charge in the carboxylate group, it's going to be slightly spread out and mitigated by the fluorines pulling on that through bond electron density. So just drawing that negative charge a little more towards themselves. So I said there were a couple of reasons that fluorine is better at this. And electronegativity is one, and it's probably the biggest reason. But the other is one that's called orbital overlap. Like looking at the effectiveness of the orbital overlap. So what I mean by that is when we're looking at the one. So fluorine is it bonds to carbon through 2p orbital. Well, okay, so it's very likely going to actually be as No, yeah, that's right. Yeah, it should just be a single bond because we're not dealing with hybridization on the part of the fluorine. Don't worry about it. So the fluorine and the carbon at any they're going to be in kind of the 2p 2s or 2p energy shell, and the carbon is also in the 2p electron shell. Okay, so I should actually explain what I was hemming and hawing about, and actually managing to say nothing. So I was afflicted by the thought of talking about hybridization for a moment, having sp orbital hybridizations as part of Vesper theory. I don't really feel like getting into that right now, so I won't. But what this is essentially saying is that the orbital on fluorine that's bonding with the orbital on carbon, that was a terrible way to set up that sentence. Let's try again. The orbitals on fluorine and carbon that overlap in order to make the bond are roughly the same size. That's better. Let's stick with that. So we're going to have this. So they're roughly the same size, and this allows for better overlap because in the case of like chlorine, for example, we're now working with like the carbon is still in kind of that 2p energy shell. The chlorine is in 3p, and so it's just saying like the chlorine is going to have a large p orbital, and the carbon will have a smaller one. I don't feel like I'm drawing good proportions on this, so we're going to try this again. And in a different color. Ha. Okay, so let's say fluorine orbital with good shading. And now, oh, come on. Okay, and the carbon orbital. So they're about the same size, and they're the degree to which they overlap, it covers like a higher percentage of the volume of the orbital, of each orbital. So this is how we measure like the efficiency or the effectiveness of the overlap. Compare that to the chlorine orbital versus the carbon orbital. and you're going to have a significantly reduced percentage of the volume of the orbitals overlapping, mostly in terms of the chlorine orbital, right? Because it's going to be a smaller subsection of that chlorine, the orbital on chlorine, that overlaps with the carbon orbital. So when you have better orbital overlap, like on the fluorine carbon bond, this makes for a stronger inductive effect, just a stronger bond in general. Actually, the carbon fluorine bonds are extremely strong. I think one of the strongest, if not the strongest, single bonds on the table. I might be wrong on that, but I'll look it up at some point. Yeah, so for both these reasons, the higher electronegativity of the fluorine and better orbital overlap because of the size of the orbitals, the fluorine is going to be a significantly better withdrawer of this electron density and make this a stronger acid. All right. Yeah, so this is going to operate on effectively the exact same arguments that we've been making. Both of these phenols will form a phenoxide that can delocalize the charge throughout the ring by resonance effects. But the difference is that the one that is the 2,6-difluorophenol is going to additionally have the inductive withdrawing effect of the fluorines, particularly because it's these ortho carbons that will carry some of that negative charge in the resonance structures. So it's going to be very effective delocalization of that negative charge through resonance and also through the inductive effect. So this is going to be our stronger acid. All right. All right. So, I vote that we take a moment and look at how cute that cat is. Here. Sorry, did I disturb you? All right. It's little Daphne. Just having a little snooze, and I have been so mean and gotten her up. But she's really cute. She's hiding her face. I think this is a very snoozy cat. Look at that snoozy little face. Hi. Want to do some chemistry? Nope. Does not. Goodbye. Oh, yes. Very good. Yes, the breaks that we take to scritch the nice floofy cats will be frequent. So, you know, you're welcome. All right. So we'll keep going for a little bit. I don't think I'm gonna stream for too much longer because my brain is fried. But we'll do a couple more. And as always, feel free to leave questions in the comments. I am always happy to talk about this or most other things. At the very least, anything sciencey, I'll be very interested in. Alright. So, rank each set of compounds in order of increasing acidity. I think maybe I'm just going to take that little text box out. Just yeah, goodbye border. There we go. Okay, better. Okay, so for this series we've got NH3, which is ammonia. We got water, and we got hydrofluoric acid. So so let's draw the conjugate bases, and then we'll use that to assess the acidity. So we got NH2, which is an amide, and OH, which is just hydroxide, and just a classic F minus, which is fluoride. Okay, so of these, there is of course no resonance stabilization whatsoever on any of these, and these are all second row elements, so we can yawn. Alright, so we can assess the acidity here by just looking at the electronegativity of the charge atom. So it's got nitrogen, oxygen, fluorine, and those actually in order are is the same order as the electronegativity. And so again, all of these have effectively one extra electron, and so the one that is most electronegative is going to be pulling hardest on all of its electrons and its extra electron, which is going to be a more stable state than one that is pulling less on the electrons, because if an electron is only very loosely held to an atom, it is that makes it highly reactive, and highly reactive things are not stable, just by definition, really. Ooh, that did not make that better. Okay, so this is in fact the correct order of least to most. The amide is the least stable, the fluoride is the most stable, so the ammonia is ammonia is the least acidic, hydrofluoric acid is the most acidic. Yeah, also you could have also just gotten to this by just trivial knowledge of, like, ammonia is a basic compound, not well known for its acidity, and then you got water, which is kind of our standard for neutrality, and then hydrofluoric acid, which it's sort of in the name. Alright, so the second series, what we're looking at is the conjugate bases are bromide. I'm going to actually be bad and not draw out the lone pairs, but that's okay, because we all know that they're there, right? Right? Okay. Alright. So for these ones, these now are not all in the same row, they are all in the same group, or the column. These are all halogens. Fluorine is the smallest, chlorine is the mediumest, and bromine is the biggest. And yeah, so when we're comparing down a group, as being group 7 or 17, depending on how you reckon it, the larger the atom on which there is a charge, the more spread out that charge is, so the more stable that charge is, right? Because in all these cases, we've got just one extra electron. Here, I'm just going to get rid of this because I'm not actually using it like I thought I would. So let's use a say. Okay, so let's say this is fluorine, and so let's say this is just dot minus. Okay, so this is just saying that the extra electron is in, you know, some orbital. It would be in a p orbital. So for chlorine, let's just label this as 2p. For chlorine, you'd be in. That is not great. Okay. So chlorine is going to have its extra electron in a 3p orbital. And then bromine has its extra electron in a 4p orbital. And so the -1 charge is in orbitals of different sizes, and that is not boron, forgive me. So in bromine, it's in this massive orbital, as it is effectively a much lower charge density, because the charge is still just -1, but it's spread over a much larger area, or volume rather. So the bromide, being the Br minus, is going to be the most stable of these conjugate bases. And the rest follow in order. Chlorine has that intermediate size orbital, and so it will be, the mediumest again. So these ones, so say 3, 2, 1, 1, 2, 3. Okay. I'm not going to bother actually drawing things out for this one, because we've got hydroxide, which is a strong base. We've got water, which is generally neutral, neutral pH, anyways. And we've got H3O plus, which is a strong acid. So I'm going to just leave it to your vivid imaginations as to which one of these is the strongest acid. Okay. Alright, so for this one, I think this one's actually kind of interesting. So, now we're going to have, again, we'll have NH2, and we'll have OH minus. But now we've got also, whoops. Now we've got SH minus as well. So it's always easiest by a long shot to compare atoms that are in the same row and atoms that are in the same column, because then we can just invoke electronegativity and size respectively. So for the NH2 minus, thank you. For the NH2 minus and the OH minus, we already talked about why the NH2 minus is less stable than OH minus. So NH3 is the least acidic. So that deals with the NH2 minus and the OH minus. So the SH minus, I'm just going to compare that to OH minus instead of trying to compare it to NH2 minus. Because then that would be a diagonal comparison, and while we can kind of do those, it's not 100% consistent, and you kind of have to just take it on a case-by-case basis. But what we can do instead, so we've already compared the NH2 minus to the OH minus. Now all I'm going to do is compare the OH minus to the SH minus, because oxygen and sulfur are in the same group, and so I can at least potentially skip a step by just looking at the stability of the ion on sulfur and on oxygen. And again, just a size issue. So the oxygen is a 2p orbital, and the sulfur is in a 3p orbital. So the negative charge on the sulfur is going to be more spread out, so that it's more stabilized. So H2S is a stronger acid. And since it's a stronger acid than H2O, we know that it is also a stronger acid than NH3. Yeah, so I feel like that one's fairly straightforward. Okay, so this one... I'll just draw out let's draw out the conjugate bases. In an alkene like this, the very, very marginally, slightly more acidic hydrogens will be the ones on like a secondary. No, that's not true, is it? Maybe on the terminal H. Yeah. Okay. All right. Never mind. So we're gonna instead take hydrogen off of the end. I mean, and to be clear, this is a small difference between a methyl and a methylene group. And they're both really, really terrible. Yeah, we'll just leave that one there for now. Draw out the other ones. Hi, Daff. Are you going to do the chemistry? Okay, y'all just need to see this. Okay, never mind. No, forget it. She's not gonna be our little circus guy. But sweetie, I do need you out of the way so I can do this stuff. Hi. Do you know you're so good? Do you know you're lovely? Very good. No, don't come with me. Okay, so where was it? Cl, CH2, and then O minus, because we're drawing the conjugate base. That, and then the third one just being just ethanol. Whoop, ethoxide, forgive me. There we go. Okay, so looking at these. So these two have the negative charge on an oxygen. This is fine. We don't mind this. This is a relatively okay situation. This has the negative charge on an alkane, and that's terrible. So that is the by far the least stable conjugate base. So it's going to be the weakest acid by a lot. Between these two, again, there's no resonance stabilization anywhere. If we formed a double bond between the oxygen and the carbon, we'd have to kick off one of the others, and then we don't have a resonance structure. So the only thing we can appeal to between these is that this one has the ethoxide has a methyl group attached to a CH2, and the one chloromethoxide, has chlorine attached, which is significantly more electronegative, and it's going to have a slight inductive withdrawing effect on the negative charge here. So the strongest acid is going to be that one with the chlorine, followed by the ethoxide, followed in a very distant third by the alkane. Alright, draw the conjugate acid for each of the following bases. I don't feel like doing that because I actually don't need a reason. Cool. Draw the conjugate base. Compound shown. Yeah, that's the same thing. This is just the same thing. Okay. So this is kind of the same thing again, but we'll go through it actually, because this is a little bit of a twist on it. So let's use uneven equilibrium arrows. What are you? Why are you like this? Just eat it if you're gonna. Don't just. Daphne brought me a little piece of spit-covered kibble. It's very sweet, and now she's drinking my water. That's my water. I'm the one doing all the talking here. Yeah, clean up your mess. No, clean up your mess. It's gross. Jeez. Okay. You nasty. Where are you going? Okay. Alright. Okay, so uneven equilibrium arrows to show whether the reaction favors reactants or products. This goes back to that that rule that I mentioned about the equilibrium always favors the side with the weakest acid. Hello. Sorry, Daphne's just like hiding in the little cubby of my desk, and it's absolutely adorable. It's my little work buddy. She likes to hang out there when I'm working. It's terribly cute. All right, just believe me. Okay, so so first, what we need to do is label what are the acid and conjugate acid and the base and the conjugate base. So the acetate or acetate is going to be our base. Water is going to be the acid. Conjugate base will be hydroxide. Conjugate acid will be acetic acid. So you can absolutely use pKa tables on these compounds and use that to figure out what's the weakest acid. Or if you just happen to know some of the pKa's, you can just use that shortcut. Or we can go through the whole process that we've been going through, which is taking the acid and the conjugate acid, drawing out the conjugate base, and assessing the stability just as we did for all the other stuff. So I'm going to use the shortcut method here because I can. So water, I'm going to have a pKa of 14, and acetic acid is going to have a pKa of about 5. So acetic acid is much more acidic than water by about 9 orders of magnitude, about 1 billion times. So that means the equilibrium will favor the side with the weaker acid, which in this case is reactants. So we're going to draw the big equilibrium arrow pointing towards the reactants and a small one pointing to products. Okay. So again, we've got the base in that horrifyingly bad carbanion there. The alkyne is going to be the acid. Conjugate acid is the alkene, and the conjugate base is the deprotonated alkyne. So looking at the two acids, again, we went over this before. This one's going to be about let's just take a conservative guess and call it 40, and the pK of the alkyne is about 25. So this means that the vastly weaker acid is the conjugate acid, because it's got that higher pKa number. So in this case, the big arrow is pointing towards products and the small one towards reactants. Alright. Okay, so this one, the acid is going to be phenol, and the conjugate base is going to be phenoxide. The base is hydroxide, and the conjugate acid is, H2O. So, what's the pKa of water and what's the pKa of phenol? I don't know. So, in this case, we're going to actually just look at the conjugate bases, which are conveniently already drawn out here. So both of these are a negative charge on oxygen, but the OH minus has no resonance stabilization, whereas the phenoxide has lots of resonance stabilization, and so on and so forth, as 1, 2, 3, 4 valid resonance structures. So this is hugely resonance stabilized, and therefore it is going to be the more stable anion, and therefore it is going to be the weaker acid. So this, is that right? Stronger acid. Yeah, the exact opposite of what I said, but I'm sure you were keeping up with that, so no worries. So this, so phenol is a significantly stronger acid than water, which means that the equilibrium arrows go this way because it always favors the side with the weaker acid. Okay. So, acid, base, conjugate acid, conjugate base. Okay, so, and I don't know pKa's of these off the top of my head, so we're just going to look at the conjugate bases. So we've got I minus and F minus. So the extra electron in iodine is going to be in the not even 4, this is going to be in the 5p orbital, and the extra electron in fluorine is going to be on the 2p orbital. So the fluoride is much smaller, which means that that negative charge is much less stable. So here's the little bit of nuance here, is that the iodine is larger, and this spreads out the charge. But there's also something to consider in that fluorine is far more electronegative than iodine. I don't know iodine's electronegativity off the top of my head, so I'm going to look that up, hopefully while I talk in something resembling a coherent manner. So there's two kind of combating factors here, which is size and electronegativity. And so we just kind of have to decide which of these is going to have the bigger influence. And there we go. So okay, so the electronegativity of iodine is 2.66, and again, fluorine is about 4. So large electronegativity difference. However, when we're comparing things down a group, it is in fact the size that makes the biggest difference. And so the charge on iodine is much more spread out, even though the extra electron in fluorine experiences overall a greater nuclear charge, an effective nuclear charge. But again, comparing things in the same group, so in halogens, means that the iodide is more stable than fluoride. The negative charge is more spread out in iodide than fluoride, so is a more stable anion, and so hydroiodic acid is a stronger acid than hydrofluoric acid, which means that the equilibrium arrows are going this way. And I don't know the pKa's off the top of my head, but they are somewhere around, like, I want to say 2 or 3-ish for hydrofluoric acid. Unless it's concentrated hydrofluoric acid, which is a different beast altogether. And hydrofluoric acid is a completely different beast from aqueous hydrofluoric acid. And is extraordinarily dangerous. But that is neither here nor there. So pK is about 2. Hydrofluoric acid, when it's aqueous, is a weak acid, whereas hydroiodic acid is something like minus 10, possibly more. It's right up there with like sulfuric acid. So it's a very, very strong acid, and so that's this is the way that the equilibrium arrows will point. Oh, so hey, that was the end of that problem set. So that, I believe, is where I'm going to call it for today. If you have any questions about anything that's been covered, by all means, leave it in the comments, and I will address it when I'm able. Other than that, I will be back on Tuesday at 7. That is April the 2nd. And yeah, so once I'm done here, I'm going to be uploading all the videos of these streams onto my YouTube channel of the same name. And yeah, all right, y'all have a good night. Okay, bye.